everyone, and thank you for standing by. All participants will be in a listen-only mode until the question and answer session. During that time, if you'd like to ask a question, you may press star 1. I'd like to inform all parties that today's call will be recorded. If you have any objections, you may disconnect at this time. I'd now like to turn the call over to your host, Ms. Sarah Fraser. You may begin whenever you're ready.
Thank you. All right. Hi, everyone, and welcome. Thanks for joining us for today's media briefing. I'm Sarah Fraser with NASA's Office of Communications. Last week, NASA and United Launch Alliance demonstrated the largest ever inflatable heat shield, LOFTID, short for Low Earth Orbit Flight Test of an Inflatable Decelerator, launched on a ULA Atlas V with NOAA's JPSS-2 weather and climate satellite. After JPSS-2 separated, LOFTID inflated, deployed, and re-entered Earth's atmosphere, splashing down in the Pacific Ocean about 2 hours after launch. Over the past week, team members have started the process of inspecting LOFTID and getting the heat shield and its data back to NASA's Langley Research Center for study. Full study of LOFTID's performance is expected to take about a year, but today we're going to hear from a few of the team members about how the demo went and what they have learned so far. So here to talk about these early results are Trudy Cordes, Director of Technology Demonstrations in the Space Technology Mission Directorate at NASA headquarters, Joe Del Corso, LOFTID Project Manager from NASA's Langley Research Center, John Donano, LOFTID's Chief Engineer from NASA Langley, and Greg Swanson, LOFTID's Instrumentation Lead from NASA's Ames Research Center. Also on the line is RJ Bodkin from the LOFTID team to help answer questions. So we'll start with some brief remarks from our speakers and then open it up for questions. As Becca said, to ask a question, you'll dial star 1 on your phone. And just a reminder that the call is also being streamed on nasa.gov. So our speakers are going to reference some images. If you RSVP'd, you should have gotten the link in your inbox to these images. The link is also posted on nasa.gov/live. If you scroll down to where this call is embedded, just above that, there's a link to the web page with those images. All right, so with that, I am going to pass it over to Trudy Cordes to get us started.
Okay, thank you, Sarah. Hi, everyone, and welcome to the audio conference today in what seems like a series of briefings we've had for you all. So thanks for your continued interest in our demonstration, our LOFTID demonstration. And I'll just start out by saying it's been a really exciting week for NASA, for the agency. And you know, we haven't had just one flight test in the past week. We've had 2. One is still in process, but to have that in common with Artemis is pretty cool. LOFTID and Artemis launching in the same week. So I just wanted to say that. You know, in technology demonstrations, we mature technologies that are in the higher TRL, technology readiness level regime. These are cross-cutting technologies with multiple applications. We certainly have that here in the case of LOFTID with both commercial and government applications for what we're developing. We do things at a system level. We put components and subsystems together at a larger system level to demonstrate them in relevant environments in which they need to ultimately operate. So these are risk reduction activities, and it's a way for us to develop new capabilities as an overall objective. And in this case, to meet the agency's future mission needs for future Mars exploration, landing large-scale cargo or humans on surfaces through atmospheres. And so that's our overall objective. Specifically with something like a technology demonstration, the basic question we're always looking to answer is does it work? Does this work at a system level in that environment? And I think last week with LOFTID, we got that answer, and it looked to be a pretty resounding yes. So, you know, we launched last week out of Vandenberg, and I don't know if any of you online had a chance to watch. It was a really cool experience for us. We had folks on both coasts, the project team and others out at Vandenberg to see the launch, and then some of us were congregated at Langley Research Center, which led this project for us. So we were in Virginia, had a watch party and watched it live on NASA TV. And I'll just say I knew this was going to play out as program director in that way, where it would be a joint with JPSS-2 on the NASA broadcast. And yet I was still in absolute awe to see it it all play out on NASA TV, and to even have them stay on with us for an extra about 45 minutes while they recovered the test article in the Pacific Ocean. And speaking of that, an image that I would point you to is image 1 on the webpage that you've been supplied the link to, and that's its splashdown. So you kind of see a glowing round article off in the distance coming down into the water. So that's a particularly cool video. So I would say last week, you're going to hear from our 3 experts today on the preliminary results. But last week I thought was just a banner day for this particular project for Langley Research Center, for United Launch Alliance, our partner, all of the participating organizations, and then Space Technology Mission Director. Could not have been more proud last week at the execution of this project. So, we look forward to the results, both the initial look at this that you're going to hear about today, and then the long-term or future detailed report that we're going to get to this in some months' time. So those are my opening remarks, and thanks, Sarah, back to you.
Thank you, Trudy. All right, next we'll hear from Joe Del Corso, LOFTID's project manager.
Thank you, Sarah. I appreciate being on, and welcome to everybody. And I agree with what Trudy said. NASA has had just a spectacular couple of weeks with JPSS-2 being on orbit, LOFTID success, and then following that up with that little rocket some of you might have seen off the East Coast, Artemis 1. Now today I'm going to talk to LOFTID first, and then I'd like to explain some of the larger context for why all these successes are so important, not just to NASA, but to the nation. So LOFTID, as Sarah mentioned before, is the low Earth orbit flight test of an inflatable decelerator. And that's an orbital entry demonstration, which is what we did. We demonstrated orbital entry of the HIAD technology, that is the hypersonic inflatable aerodynamic decelerator technology. For anyone who still doesn't know what HIAD is, it's a deployable aeroshell that's stowed for launch and during cruise, then deployed in orbit prior to atmospheric entry in order to decelerate payloads at destinations with an atmosphere. So LOFTID was flown as a secondary payload on the Atlas V launch vehicle. After the Centaur, the second stage of the Atlas vehicle, delivered JPSS-2 to Earth orbit, the Centaur stage then fired deorbit motors and began deorbiting the LOFTID vehicle. If you look at the images on number 2, I believe they're referenced, you'll see some of the activities that we were able to see shortly after downloading all the video of the aeroshell inflating. So the Centaur second stage deorbited the LOFTID vehicle, turned the vehicle on, inflated the aeroshell, and then released the LOFTID reentry vehicle. LOFTID entered the Earth's atmosphere at 8 kilometers per second, which is right on point with what we were expecting. And we were able to track the RV, the reentry vehicle, all the way through splash from both ground and aerial aspects. So both John and Greg are going to talk a little bit more about that. While we're still currently in the process of downloading all of the sensor data, converting it to usable information and engineering units, as well as the visual and the IR videos, we can safely say that based on the recovery of the RV, some of our quick look data and the state of the aeroshell and the information that we do have, that the demonstration was a huge success. Now, putting all this into larger context, with the success of Artemis 1, NASA has now demonstrated the United States' new heavy up-mass capability. In order to put people into space on the moon or send them to Mars, we need stuff, lots of it, which means we need to put a lot of mass into space. NASA has now demonstrated that we have the capability to put heavy payloads into space. On the flip side, with the success of LOFTID, we have now demonstrated the HIAD technology. In other words, NASA has demonstrated the United States' new heavy down mass capability. We have now the ability to both put heavy payloads into space and to bring them back down. These two successes are huge steps in enabling human access and exploration. We're going to space, and we want to be able to stay there. Back to you, Sarah.
Thank you so much, Joe. All right, I'm going to pass it next to John Donano, who is LOFTID's chief engineer.
Okay, hello, welcome everyone. I couldn't be happier with the way this mission went and with what we're seeing so far. We are all eager to get the data, all of the data, the comprehensive set of data off of the vehicle, and we're in the process of doing that, but that process will take a considerable amount of time. So I'm going to speak to what we have seen so far and what we have learned from it. So we had the data from the Centaur, and that revealed that our trajectory was spot on. We were delivered right on target at the proper entry orientation, the proper speed and flight path angle. We saw the initial external infrared imaging that was referred to in image 1, and it did, the heating on the outside of the air shell looked uniform. It did not reveal high heating concentrations from what we could see in that video, and that suggests good uniform performance. The outside of the aeroshell, when we recovered it, looked absolutely pristine. The aeroshell and the center body, you would not know that they had been through a very intense reentry pulse. It was well protected by the heat shield, and it looks as if the inflatable structure could fly again. The forward side looks nearly pristine as well. It did sustain some damage, but nearly all the damage on the forward surface of the air shell appeared to be caused by a splashdown and time in the ocean, things that it wasn't really designed for. The process of pulling it out of the ocean and setting it onto the fixture, it sustained some mechanical damage that way. But we did not see damage from heating or from flight on the air shell at all. We saw some minor markings on it that suggest some streamlined flows, but nothing that actually would come close to penetrating through the protective layers. The water, it had made the forward layers heavy and applied loads in the opposite direction for the intended design in flight. So this damage wasn't surprising, and we knew that risk going in, that it could sustain much more damage than we actually observed. So we're very happy with the resulting vehicle that we retrieved from the recovery ship. And Greg will speak to some of the processing on that after we recovered it. We did download video data from the uplift camera, and those, if you look in the packet online, that would be item number 5, which is that's the money shot for us. The view of the reentry plasma is it was incredible to watch. And item 6 shows how stable we were with the descent and the parachute deployment. So this uplift camera is a camera at the aft end of the vehicle, looking up behind the vehicle through a protective window, and it showed terrific images of the clean separation from the Centaur. And we could observe the Centaur doing its collision avoidance maneuvers as we drifted away from it. And then it gave us these amazing images of the plasma wake behind the vehicle. It first begins as glowing softly orange, and then it becomes much brighter. And you see the wake field converge towards the center, well behind the vehicle. And this convergence stayed remarkably well centered in the camera view, and this reveals qualitatively that the vehicle is very stable. The orange color then transitioned to an intense blue color from the heating, and the plume, you'll see, includes an axisymmetric pattern, kind of like spokes on a wheel, that coincide with physical features on the aeroshell, and all that looks nominal. And then we also found that, in the video number 6, the descent and parachute deploy, that the moon happened to be framed nicely in the middle of the window, and that stayed there throughout its descent through transonic and subsonic flight, proving that the vehicle is very stable in all regimes. And that was a wonderful thing to demonstrate. It's hard to get that completely demonstrated on the ground, and so this flight proved a lot of people right. So the uplift camera saw the parachute deploy in darkness, but we're working on ways to enhance that and see it a little bit better from the images it captured. and it was picture perfect all the way down to splashdown. So I guess the natural question is, what's next? We've seen, a very successful mission here, but we still have a tremendous amount of data to work through and to process. We extracted the internal data recorder from the vehicle, and we retrieved the ejected data recorder from the ocean. And so we now have to go through the comprehensive data that was recorded on board. And this includes thermocouples, pressure transducers, heat flux gauges, load cells. The inertial measurement unit is a big one that will help us with the reconstruction of the flight. Fiber optic sensing system. This is its first flight, and we're hoping to get a good map of temperatures in different locations. GPS data, we have avionics housekeeping data on board, and obviously we have the video and the infrared cameras that will help us with the onboard imaging, along with some external imaging data from the SciFly team that were airborne and tracked the reentry of the vehicle coming in. And so they got the performing the SciFly LOFTID imaging mission, were able to capture that. So we do have the data downloaded from the data recorders, and it's being processed now, but it will take some time to go through it all and make it usable. And we extracted the single board computers from the camera pods. They were physically extracted from the vehicle and have been sent back to Langley, and they are being processed for eventually getting higher definition images from the onboard cameras. And we will be using all this data to assess the reconstructed trajectory. We'll be correlating our CFD, or computational fluid dynamics, entry environments. We will be examining the inflation system performance, the structural performance of the aeroshell itself with the internal pressures and load cells against those applied environments, and of course the thermal response performance, which is one of the major items we want to get from this. So that's all I have for where we are right now, and I'll pass it back to Sarah.
Thanks, John. Okay, next we will hand it over to Greg Swanson, LOFTID's instrumentation lead.
All right, thank you, Sarah. So as everybody was sitting at Vandenberg for the launch, and the rest of the team was sitting at Langley for all the festivities, a small team of us, were out on the Kahana 2 vessel out about 500 miles off the coast of Hawaii, waiting in the recovery zone to be able to recover the article and ejectable data recorder after splashdown. So we got out there about 2 hours before launch and started doing preparations to recover the RV. The goal was to go get the RV first because that was not designed to float, whereas our ejectable data recorder was. So we first positioned ourselves in a good place to recover the re-entry vehicle. Had a lot of excitement on board when we started getting the data packets, and then of course the IR imagery that Trudy pointed to in the beginning. That was amazing to see the thing come down under parachute and splash down. And once it was splashed down, we actually could see it with the naked eye, the lights on the vehicle, and so we were able to really easily point the recovery vessel, the Kahana 2, towards the re-entry vehicle and head that way. It was less than 5 miles away, so it took us about 40 minutes to get there. As we were getting there, we were getting everything prepped and ready to get in the water. So we put on the big recovery vessel, there was also a small boat, a 7-meter boat that we put into the water using the large boat's crane. And a small group of us, 3 of us from the LOFTID team and 1 crew member from the boat, headed out on that small boat and pulled up to the recovery, or the re-entry vehicle, which I have to say was one of the most amazing things I've ever done in my life. I mean, pulling up to see something that we've worked on for all these years, just floating there high in the water, no water in the basket. It looked pristine, like it hadn't even flown through space. I mean, that was truly amazing. So once we got to it, we pulled up next to it and we were able to hold on to it. Actually, if you go to video number 8, That's a quick video of a camera I was wearing on my head. You can see me actually holding on to the vehicle as Steve Hughes, the aeroshow lead, is prepping the parachute legs. We had the parachute was designed to, once it hit the water, to release the actual canopy, and so we had the legs left, and that's what we were able to use to lift it onto the recovery ship. So Steve Hughes is putting the shackles onto those recovery legs and then getting it ready. And so once we had all of it rigged up, we were able to attach the lifting point to the big ship's crane, and they were able to get it on to the recovery vessel and in the stand that we had created to bring it home on the boat. After that, it was still dark. That whole process took a couple hours. We waited until daylight to go after the ejectable data recorder. That's our little data module that is about the size of a large lemon. It's also painted yellow, so lemon's a good analogy there. But there's no lights or anything besides it's sending us its coordinates, but besides that, we have no way easily to see it without just spotting it in the water, so we wanted to wait till daylight. So once the sun rose, we went after that, and after a few passes, got that on board and headed back to port. Now that we're back in port, you can see, if you go to video 9, that's a time lapse of some of the activities we're doing. And it starts with us lifting the RV off the Kahana 2. We placed it over near University of Hawaii's Marine Center warehouse, where we've been working on it and inspecting it. You can see in that video, the first thing we do is we did some inspection, and then we deflated it. And once we got it all the way deflated, we were able to go in and remove the panels, remove the system batteries and the internal data recorder. And it was great to get all that out. Once that was done, we lifted it and put it on its side. You'll see that in the time lapse as well. And we were able to pull then all the camera single board computers that John talked about and the upload camera footage, and that's when we first got to see that, which was also amazing. After that, we put it nose up and reinflated it, and we did one final inspection, a detailed photo survey of both the forward and aft side of the vehicle. And yesterday we deflated it one final time, and this morning we got it all wrapped up and packaged and shipped and ready to ship back to Langley. And that's where we're at. So I'll give it back to you, Sarah.
Thanks so much, Greg. All right, so that is all of our speakers. So we are now going to start the Q&A portion. So as the operator told you, when you're ready to ask a question, if you press *1 on your phone, that will put you into the queue. And when you do ask your question, please state your name, your affiliation, and to whom you're directing the question if it is for a specific person. All right. I think we are ready to start the Q&A, so I will let Becca call on the first person.
Our first question comes from David Curley. Your line is now open. You may ask your question.
Thanks very much. I guess this is for Joe. You suggested that maybe the inflatable part could be reused again. I've never heard that that's a possibility. Are you now considering it, or was that always part of the plan? By the way, congratulations. You all sound extremely excited. And Joe, I think you said it, the breakthrough that this really is, that I'm not sure how much attention it's gotten across the industry. And what does ULA have to say? Thank you.
So, thank you. So as far as the first question, Dave, thank you for the congratulations. I really, what I typically do is I point to the team. I say, look, this team has been spectacular. They've done a great job. So we're all extremely excited. When it comes to the breakthrough of the technology itself, ULA is very excited. We've already got Space Act agreement in place or about to be in place. We're working on final signatures now for their smart reuse. They have clearly been very excited. They want to utilize this as part of their engine recovery operations. So, we were standing there in the LVDC-1 as we were seeing the vehicle splash down, and John Reed, their chief engineer, chief rocket scientist, was calling into the ULA folks and saying, hey, this is a spectacular success. So all in all, everybody is incredibly excited. As far as reuse of the inflatable structure, we're really designing these as single use, but we have looked at dual use, such as aero capture to entry. We just haven't validated a dual use application yet at this point. While the aeroshell is pristine and beautiful, we've got some work to do to really analyze to make sure that, hey, would this work in a dual use capability situation? Thank you.
Our next question comes from Jeff Faust. Your line is now open.
Hey, good afternoon. A question probably for Trudy. What is the next step in testing this technology once you're done analyzing the data from LOFTID? Is NASA planning to scale up and test larger inflatable decelerators, or hand this technology over to industry for further development? Thanks.
Yeah, hi Jeff, thanks for the question, and the other folks online might want to jump in as well. But yeah, so at the agency level, we have roadmaps for each of the capability areas that we're developing, and this is in the entry, descent, and landing category, as you know. And yes, you're right, scale up would be a next step for us. The agency for its future Mars missions is talking about, it hasn't been finalized, but is talking about scale up of this technology in the like 18 meter range, 18 to 20-ish meter range. So there's quite a bit of work that needs to be done with that. There are facility considerations with that need to be looked at. But the roadmaps will guide us on that in our the future investments in that, and we're taking a look at that now, and will in the short term future for that. So yeah, that would be next step for this capability. I don't know if anyone else online wants to add anything else to that response.
Yeah, this is John. I can add to that. Thank you, Joe. Sorry. This is the largest blunt body that has ever re-entered the atmosphere. So this, we made this about as large as you possibly could for the constraints that we had as a secondary payload inside the Atlas. We are, but yeah, the next step is to scale up even beyond this, and we'll need to for the Vulcan engine recovery, and certainly for missions to Mars. But this 6 meter diameter was a really large step from what had been demonstrated before, and nothing had been demonstrated as a system at this level of energy from orbit. So this was a very good, unique stepping stone in that process to demonstrate a very mission applicable environment that is it is an example of what we would do for Mars missions or robotic missions, even at this scale. But we do have a lot of work to do going forward as well for all the applications we have in mind.
And just to chime in real quick, this is not a NASA or industry. This is really both NASA and industry moving forward. Industry has applications for the use of the technology. NASA, as Trudy mentioned, has roadmap for use of this technology for scale up and eventual use at Mars, and even more in the near term for Earth entry as well. So this is not an either or; it's definitely an and.
As a reminder, if you'd like to ask a question, please press star 1. Our next question comes from Kenneth Chain. Your line is now open.
Hi, thank you. So I'm wondering if the analysis follows through and everything worked as well as you think it does, what would the TR level be? And is it ready to actually be incorporated in NASA mission? I was thinking it would be really useful, for instance, on Mars sample return, where it's been, the current technology is sort of at the limit of what the mission is at. Thank you.
So, Trudy, do you want to answer this one, or you want me to take a shot?
You can take a shot, Joe. I'm sorry, the speaker was breaking up quite a bit for me. I'm not sure I heard the entire last part of the question, but yeah, Joe, if you want to start.
Okay. So the question that I heard is what TRL do we think we're at? What technology readiness level do we think we're at? With the success of LOFTID, I would put us, firmly at TRL 7 at this point. We do still have a lot of work to do when it comes to scale up, and so we'll have to continue to do some ground activities as well as flight demonstrations just to show some of the capability at larger scale. But a lot of that work has already started and was started under the HIAD 2 ground development effort when we scaled up to 12 to 16 meter scale, and we demonstrated that we had the capability to build to that. Now, there's still a lot of work that has to be done, but just kind of throwing, squinting my eyes and blurring my eyes and putting my thumb out there, I would say we're right around TRL 7.
Yeah, thanks. I didn't hear all your questions, so thanks for that, Joe. I would answer the same way with the TRL level, and I think the second half might have been something about, is it ready to be incorporated into NASA missions? Certainly, if there are NASA missions that can use this, this scale, but we have to remember this is it's a learning for us. This is a flight test. We have to take some time to really understand what the hardware experienced, and kind of wait for the team to do its forensics on this and do their data reduction and issue the report on this before we can really figure out the go forward plan here. So it's a great step, but we do have some work to do in the coming year to be able to look at all this and learn from it.
Our next question comes from Marcia Smith. Your line is now open.
Thank you so much. And I'd like to follow up on Ken's question. I think he was asking specifically if you might use this on Mars sample return. And I think more broadly, I don't think I've heard how much mass you could land on Mars with a 6-meter diameter shell. So in terms of what's the next step and scaling it up, the 20-ton limit that I've heard before about how much is needed if you're going to be landing humans on Mars, that, does a 6-meter do it for humans, or do you need to scale up to 18 meters? Just how far does this get you in terms of utilization on Mars? And a second question unrelated to that is, was it something special about launching this out of the West Coast? Can this be launched from either coast?
John, do you want to take the mass?
Yeah. So this is John Donato. Regarding the mass at Mars for a 6-meter, I don't have those numbers directly in front of me. I would think it'd be somewhere on the order of 2 tons. Regarding the launching on any coast, yes, we could. The reason we were on the West Coast this time was only because of the ride share that we were on, and they were going on a polar orbit. So that's why they launched out of the West Coast. We could, we stow in a vehicle and can launch anywhere as long as we get our flight path correct for the reentry.
And how much would you need to land humans on Mars? What diameter aeroshell?
I think Trudy was speaking to that. That's on the order of 18 to 20 meters.
Yeah, I've heard numbers from our counterparts in exploration systems in the range of 18 to 22 meter diameter HIADs. And you might not want to quote me on that, maybe 18 to 24, but it's in that realm of probably scaling this up times 3 is 3 to 4 is what I would guess. Yeah.
And the question about using it on Mars sample return?
Yeah, we have not had those discussions with Science Mission Directorate at this point. So that is not a discussion that's taken place yet with our colleagues in SMD.
Thanks so much.
All right, just a reminder, this is Sarah again. If you want to ask a question, please press *1 to get in the queue. I don't think we have any more questions at the moment, so I'm going to ask one of my questions, and this is for anyone who wants to answer. Can you tell us something about what was surprising about the flight demo? Was there anything that was unexpected for you?
This is John. I'll go ahead and try since no one jumped in. For me, I was pleasantly surprised with how nominal the flight was. We had prepared for, dispersions in the trajectory, and everything was right down the middle to the point where we could see the article coming down undershoot from the ship. I was not expecting that. I didn't want to allow myself to expect that. As engineers, we're always trying to think of how things might go wrong and how we mitigate against those. And so you don't get comfortable assuming a nominal flight, but I was surprised by how nominal it was. It was right down the middle.
And I would just say, Sarah, from just a casual viewer, which I was that night watching on NASA, the NASA broadcast with a lot of other people, I was surprised at how the proximity in which the test article landed with respect to the recovery vessel. That did surprise me somewhat. I did know that the recovery vessel was within the ellipse of the landing ellipse, but still how close it landed was surprising to me, and I think probably speaks to our expertise in trajectory analysis and those folks who do those things. So that was great.
Yeah, and I'll say from my perspective, just seeing the article, post-flight, we had a lot of preconceived notions going in. When you look at the data for long periods of time, and you look at the expected, heating environments and entropy environments, and as John said, you plan for all the dispersions, you kind of get sidetracked in some ways. So when the vehicle came in and we looked at it, I expected charring, I expected some, brown spots, I expected the aft side of the vehicle to have some indication of, significant heating, but the vehicle looks just beautiful. It looks pristine. And I really can't say that enough. It was surprising to me how good the vehicle looked. So that was to me the biggest surprise out of all of it. Yep.
Yeah, to expand on what Joe just said, that's one of the things that going into this mission, an area of the highest uncertainty, you can't really get it from ground tests. You gotta fly these missions to confirm, is the heating on the aft side. You get some recirculation flow from the hot gases in the plasma, and there's a concern that recirculation can concentrate in a certain area. We will be assessing data for that, but the qualitative observation is indeed, like Joe was saying, looks pristine. And our principal investigator, Neil Cheatwood, had predicted a lot of these things that we're now seeing, and it's great to see that he was right about so much of it.
All right, thank you. We do have a couple of press questions in the queue now, so I'll turn it back over to Becca to call on those folks.
Our next question comes from Mr. Mike Wall. Your line is now open. You may ask your question.
Thank you all for doing this. Mike Wall from space.com. Just a quick question. If you want to scale up to say the 20-meter range with the HIAD, if like that's a legitimate next step, I mean, can you test a vehicle of that size with a reentry test? Like you did with LOFTID? Are there rockets big enough do that, or is this just something, and if you can you say that that's the next step that you're working toward? Are you actively trying to kind of line that up as a next step for the high ed program? Thank you.
So if it's okay, I'll take a stab at this one. Yeah, so scaling up to 18 to 20 meters is definitely one of the areas that we are looking at. Our biggest challenge on the JPSS-2 LOFTID launch, as John mentioned, was we were limited by up mass, we were limited by volume, so we had to scale the reentry vehicle to a size that we could fit within the available up mass and volume that JPSS-2 was allowing us to have. When it comes to getting to 20 meters, when you start talking about like 18, 20 meters, really what you're talking about is bringing back, say, a Cygnus capsule or one of the elements of the International Space Station. That is something we've looked at in the past, but even then it doesn't quite get to the mass that we really need to demonstrate 18 to 20 meter scale. So, when the best I think we could do at this point is probably trying to bring back one of the elements of ISS or a Cygnus module with the say like one of the orbital missions. But even then, we're only going to be able to bring back 10 to 12 meter scale or test 10 to 12 meter scale. We really need a heavy mass to bring back in order to get to relevant conditions for 18 to 20 meters.
Yeah, Joe, just to add to that, sorry, I'm so excited about this. I like talking about it. But I think your question was spot on. You asked if there's a rocket or a launch vehicle that is big enough to accommodate an 18 meter or a 22 meter. And that is what's so advantageous about a high ed. We can compact it into any shape, almost any shape. And so we can compact it down into whatever the launch vehicle needs us to fit into. Just take the room that we need to for the packed aeroshell, not the full 18 meters.
Great, thank you.
Our next question comes from David Curley. Your line is open.
Thank you for another question, and I'll let you guys decide who wants to answer. Two questions, really. Scaling sometimes brings challenges. What are the challenges when you want to scale 3 or 4 times from your test article? And a lot of you have worked on this for a long time. Can you talk about the arc of the ideas of a high ed? And we've seen some work, but to get to this point with the technologies, the fabrics, and everything else, just give me a sense of the bigger picture of that arc. Thank you.
Yeah, so I think I can talk to the arc, but then I'd probably want to hand it over to Greg or to John to talk about some of the challenges of scaling up the technology. As far as the arc, we started obviously back in 2003. Very early on, low technology readiness level, doing just very crude and elementary testing in wind tunnels. We looked at a wide range of materials, wide range of layups, evaluating test facilities, and in a lot of ways we were really learning how to actually work with flexible systems, which is what the high ed technology is. It's a big flexible system. As we've matured over the years, the tools that we use have matured. The material systems have become much more mature. The construction techniques that are used have become increasingly not just more complex, but much more mature in how we handle materials. And so when you say the arc of what we're looking at, we have a wide range of upcoming materials that are being fed from our GCD, our game-changing development folks within STMD, our stakeholders at headquarters that feed new materials, new systems, and new ideas into the Hyatt technology arc, if you want to call it that. So we are constantly in a state of evaluating new capabilities, new materials, and then developing new methods for verifying material viability for the application that we're using it, which is taking a material, compacting it to small volume, and then letting it sit in vacuum for extended periods of time, and then putting it through a giant heat pulse and pressure load during an entry phase. So you take all that together, and it becomes a big smorgasbord of work and ground development that ultimately leads to demonstrations like LOFTID. I'm not sure if that necessarily answered the question, but I'll hand it over to John and Greg to talk to either that or some of the challenges for getting to larger scale.
Yeah, Greg, I think you can speak to this better than I can. So Greg is announced as our instrumentation lead, but he's also an aeroshell subject matter expert working with Steve Hughes, our aeroshell lead, and has firsthand knowledge on what it takes to manufacture these inflatable structures and flexible thermal protection system.
Yeah, thanks, John. So yeah, I mean, there will be challenges. With the 6 meter size right now, we do a lot of things just with human force. I mean, a lot of these materials, it's all a soft goods construction. So all these materials are alone, a lot of them can be somewhat delicate until they get manufactured into the full assembly. And so one of the things is right now, most things are done by hand. Most things are moved around by hand, things like that. Once we get to these larger scales, we get these larger swaths of material that we're going to be using. And so we're going to have to be careful how we do our assembly to not put added strain onto these materials as we move them around and things like that. So there's a big challenge just in the actual hands-on fabrication. There's also, material limitations in the width of what we can get. And so some of these materials, we have to get a little bit more creative, how we do our manufacturing processes. And I can't really go into detail there, but we'll have to get a little bit more creative. And we have actually looked at this in the past under the HIAD 2 development ground test campaign. We actually built the first 3 tori of a 12-meter design. So it wasn't a full 12-meter assembly, but it was the first 3 tours, which I think came out to about 7 or 8 meters, somewhere in there. And we learned a lot there because those had a section diameter. For LOFTID, our section diameter was for the smaller size of the tours was 15.7, and these other ones had that we did a while ago were 24-inch minor diameter of the tour, so 24-inch wide tube, and that was really good experience for us, gave us a lot of ideas on how to do these manufacturing steps as we move forward. One of the things is with the ULA Smart Reuse that we're working towards with our partner ULA is the engine recovery, and that is going to be on the order of that 10 to 12 meter size. So that is a near-term step that we're working towards.
Yeah, and one other thing on that, I want to introduce RJ Bakken, our reentry vehicle lead. He could probably speak to, there's also challenges associated when you scale up with the inflation gas, the amount of gas you need to get it into shape and maintain pressure. And we've been looking at developing different ways to inflate aeroshels that are beyond what we are using in these flight demonstrations, which is a blowdown system. So RJ, I don't know if you want to speak to those challenges.
Sure, John, thank you. We've been working with various SBR contractors for a few years, but we've been using blowdown systems because up to now we've not really focused in on some of the support architectures. And when we do our trade studies, looking at humans to Mars and some of these other commercial entities, we believe gas generators are more efficient from a mass standpoint, from a processing standpoint, and we've been trading various gases and how we can store those gases as solids to increase the mass efficiency, and then also remove some of the potential failure modes, regulators and control valves, and some of the infrastructure we've used on going back to RV2 and RV3 all the way to LOFTID. And so we're just getting to the beginning of starting to invest in those particular technologies, and there's not a lot of existing technologies out there that meet all our requirements. A lot of them have negatives like high water content or high temperatures, high carbon content after you fire them. So that is an area that we are starting to invest in, and is an enabling technology to support the larger scale HIADs.
Thank you, RJ. Just real quick, I wanted to follow on what Greg was saying earlier about some of the other challenges. If any of you have a tape measure, just go outside, measure out what 12 meters is, measure out a distance of 20 meters, and then one of our big challenges is that a lot of our facilities and our vendors that we work with are going to end up having to change facilities in order to build articles to the size and scale that we need for human access to Mars. So it is a challenge for NASA to work with vendors and to that have worked with us for years to develop the technology. But it's kind of the next major step. And when you look at 12 meters and 20 meters, if you go outside and you do this for yourself, you'll see the facilities that you need to handle materials and layups and systems that large are huge. So, that's another one of the just physical limitations and constraints that we're going to be working within.
Thanks all. We have a couple more questions in the queue, so I think that'll probably be it for today. I do just want to say, since we had RJ answer that for those on the line, that was RJ Bodkin, Bodkin, and he is the reentry vehicle lead for LOFTID at NASA Langley. All right, Becca, on to the next question, please.
The next question comes from Kenneth Chang. Your line is now open.
Hi, I hope you can hear me better this time. So one of the reasons people sort of have hesitation about inflatables is worrying that it won't properly inflate or that it'll pop. So I was just wondering, what else do you need to do to sort of demonstrate the reliability this will work basically every time? Thank you.
So, John, I'm going to hand this over to you, but I'd like to say something real quick. I had a question very similar to this asked of me at a technology day on the Hill many years back from an astronaut asking, do you really think humans should be putting their lives on inflatables? And I didn't know who he was at the time, and I kind of very offhanded, snarky comment that came out of my mouth that shouldn't have was, well, why not? I mean, billions of people put their lives on inflatables every day. I mean, that's what the wheels on your car are. So it's I don't mean that in quite the facetious way that it came across, but the reality is that we use inflatables and inflatable structures for a number of different applications, and this is just a very specific application for our inflatable systems. John?
Yeah, so we do a lot of preparation for how to maintain inflation of these articles, how to make them as leak tight as possible, and they are incredibly resilient and strong materials. One thing I want to clarify is a lot of times we say this is a flexible system, and people might walk away with the wrong impression there. It is flexible in the sense that we can deflate it and fold it up and pack it into a smaller diameter for flight. And then, but when it's deployed and when it's pressurized, it is a very rigid structure. It does not take too much pressure to make it rigid, but this is not, it behaves much more like a rigid heat shield in flight. It's not as flexible as you might think. The other thing is, yeah, I see this as akin to, and this is one of the reasons I'm so excited and just incredibly grateful to our team, so many people involved in making this a success. This is akin to a parachute. If you're talking about a soft good that handles, missions that include people. And we've demonstrated that over and over again, and parachutes have become very reliable and safe. And that's where we're headed with this. This is akin to a first successful parachute test in a different regime, an inflatable heat shield, which if you asked me 10 years ago, I'd be like, that's crazy. But here we are, and it works great.
Thank you. Before we go to our last question, which we'll have to answer quickly, I just want to give a few closing pieces of information. So first of all, there will be a replay of this call available on the phone line, and I will send that information to those of you who are dialed in. For anyone listening, it'll also be available at the YouTube link that is currently embedded on nasa.gov/live. And if you have any follow-up questions or interview requests, please feel free to reach out to me, Sarah Fraser, sarah.fraser@nasa.gov. And now I will hand it over to Becca for our last question that we will answer quickly.
Our last question comes from Marcia Smith. Your line is now open.
Thanks so much for letting me ask a second question. And it's actually two questions, but they're quick. The first one is, how much did this cost? And the second one is, when you're doing this at Mars, of course, the Mars atmosphere is completely different from Earth's atmosphere. So do you know enough that you can do it through modeling to know how this is going to perform in the Mars atmosphere, or do you need to do a test first?
Yeah, so
Hi,
go ahead, Trudy.
Joe, I was going to take the first question, and then you all can take the modeling question. So, Marcia, thanks for the question. The cost of the LOFTID project, 5-year duration project, was about $93 million. And just to clarify, about a third of that was hardware in the $30 million range, and future versions of HIAD, depending on what the application is, we estimate, because you're getting rid of the non-recurring engineering costs that are in there that you don't need to pay for again. We estimate in the $2 to $5 million range. So I hope that was helpful. And Joe, then if you could take the second question.
Yeah, actually, so thanks, Trudy. As far as the second question is concerned, yes, we definitely know enough about the Martian atmosphere. At the surface of Mars, the atmosphere is about the equivalent of what we have here at Earth at 100,000 feet. As my PI would say, if Mars had any less of an atmosphere, we would say it didn't have one. John, do you want to say anything more about that?
Sure, yeah, thanks, Joe. This test was a very Mars-like trajectory. We targeted the upper atmosphere and a shallow flight path angle at this velocity and this ballistic number to simulate what we have analyzed for Mars. So it has applications for return to Earth, obviously, and we demonstrated that, but this also has direct application to the environments we see in Mars. About the only difference would be the species of the gas itself. The chemistry at Earth is different than of the atmosphere at Earth is different than the chemistry of the atmosphere at Mars. But we did fly a very similar trajectory mechanically through the atmosphere.
And just to follow up on that, when we flew Medley and Medley 2, we did characterize species of gases at Mars. So we're very, very aware of what those chemical species are at Mars. So and the modeling for that has been validated.
Yeah, correct. Good point, Joe. We know how to account for that. So we have we'll have this flight correlated data to put into our models, and we will have a very Mars-like entry.
And let me just clarify on the question, your first question, Marcia, was the $93 million I quoted to you, that's the NASA side of the cost. Does not include combination with, there doesn't include any ULA costs in there, so that was strictly NASA.
All right, thank you so much, everyone. That is all the time we have for today, so we are going to wrap up here. Thank you again for joining us.
Thank you, everyone, for your participation. That concludes today's call. You may disconnect at this time.